Continuing with our treatment of single variable searches, we will now look at the Fibonacci search method, which basically works on the Fibonacci series. If you recall, in the last class we wrote the algorithm for any number f of n in the Fibonacci series. So the first number is 1, right? Okay, 1. Right. So we use the Fibonacci series in order to divide the interval and choose 2 points. Please remember that always in a single variable search we use a 2-point test. We find out whether y of x1 is less than or greater than y of x2, and accordingly a portion of the interval is eliminated. So Fibonacci search method is yet another elimination method, okay, where a portion of the interval is eliminated. It is called an elimination method or a region elimination method. Okay, please recall that in all these elimination methods we are just looking at whether y of x1 is less than y of x2 or y of x1 is greater than y of x2, regardless of how much these values have changed with respect to the previous iteration. Obviously you can conjure up with visions of coming out with some algorithm which can do better than this. That is, if you take into account the nature of variation of the objective function also, how these vary, then it is possible to come out with better single variable search algorithms, but that is not the intent of the treatment, at least in today and tomorrow's class. Without having to worry about how between 2 iterations how y of x changes, we are always looking at the 2-point test and seeing whether y of x1 is greater than or less than y of x2 and removing certain portion of the interval. So it comes with a certain efficiency and it comes with a certain price, right? The price is the computational cost. Now what is the strategy? And I think in the last class I told you I took an interval where x varies from 0 to 8 and we divided the interval such that x1 equal to 3, x1 equal to 5 and x2 equal to 3 or whatever, and then we subdivided and we figured out that one of the 2 points in every new iteration is already a old point, in the sense that it was a point in the previous iteration, okay. So in the execution of the Fibonacci search, every time you have a 2-point evaluation there is only one new point. The second point is already an old point. Therefore even though the interval is not reduced by 50%, because you are evaluating only one at a time, asymptotically it has a convergence rate which is far superior compared to the dichotomous search method, okay. Now what is the strategy? Okay, so needless to say we are considering a unimodal function. As usual we start with an original interval of uncertainty of I0. X equal to A, x equal to B. Okay. So we choose 2 points. I1 and is also I1, correct. Should I use different chalk or is it fine? I meant different colored chalk, differently colored chalk. This is a simple 2-point test where we are having 2 points which are symmetric, about the endpoints, Now what is this I1, right? So there should be a strategy for getting I1 from I0, okay. I1 is equal to I0 by 2 approximately, if epsilon tends to 0, that is a dichotomous search, okay. But what is the relationship between I1 and I0? That is the algorithm, right. For the Fibonacci search, the algorithm is okay. So you choose a particular n. How will you choose a particular n? Finally, we will have to figure out what is the reduction ratio of the algorithm. For the reduction ratio of the algorithm, which relates the I0 to In, you know the original I0. So suppose we specify the final interval, final accuracy level of the interval of uncertainty, you will also know what is In. So knowing I0 and In, you will know the reduction ratio. The reduction ratio should be a function of n or should be a function of f of n. So you will be able to get f of n or n. If you are able to get only f of n in the first place, from f of n you will get back your n. You start backwards and work like this, because in a computer, when you are writing a computer program, you will not do like, so for purposes of exam or for purposes of class, I say 6 evaluations, 8 evaluations, 10 evaluations. We do not do like that in a computer program. You do not say do I is equal to 1 to 100 iterations and stop a program. That is for starters, to check whether a program is working. Who has told you that within 100 iterations the solution would have converged? You will see whether it works for 50, 100, 200, whether there is a math overflow, blah blah. Then you put your convergence criterion. Like that, when I say do 6 evaluations, 8 evaluations, it is for demonstration purpose in the class. When you actually write a program, you will work backwards. For this system, I want an accuracy of this much. Then you start backwards and find out, and then you will find out how many evaluations are required. All right. I1 is equal to I0. So this is equal to. So it is lighting up now. Okay, so I0 B minus A fine. So can we write x1 and x2? x1 equal to A plus all right, with dynamical adjustment of to find out whether Venu, Rohit and all these people are. This is the algorithm devised by Web Studio people. Okay, so x1 is A plus B minus A into f of n minus 1 divided by f of n. All right, x2 equal to B minus, correct? Correct? Vikram, is it all right? So early morning you should be up on your feet. Immediately you should not wait for me. So f of n is the denominator, you have to cross multiply A into f of n. F of n can be written as f of n minus 1 plus n minus 2, you can get B minus A, you can subtract certain things and simplify, correct? All right, you can do that. So x1 equal to A yeah, can you tell me, can you simplify this? A f n minus 1 goes off, right? So x1 equal to good A f n minus 2 plus B yeah, this is just exploiting the property of the Fibonacci sequence. Let us call it 3. Similarly, Is this step clear? I rewrote Fn as Fn minus 1 plus Fn minus 2, that is the property of the Fibonacci sequence of the particular number Fn in the sequence. Similarly, minus so fortunately x2 is b Fn minus 2 plus a Fn minus 1 and x1 is, otherwise we have to go home. If x1 is equal to x2, there is no 2-point test. So if you get the same expression for x1 and x2, go back and check your algebra. This may happen eventually when the 2 points coincide, then you get RG. So finally when it reaches there is only 1 point, that is okay, but not when n is sufficiently large. You should have x1 should be different from x2, it is alright. So x1 and x2, then you do the 2-point test depending upon whether the function has to be minimized or maximized. You will eliminate the region to the left of x2 or the region to the right of x1, right, nothing great so far. It is like any other algorithm, right. No great shakes till now. The beauty comes in the next iteration. Okay. Now for purposes of demonstration, we have to take a call on whether region to the left of x2 or the right of x1. I always like the left hand side. So we will eliminate we will assume some y such that the region to the left of x2 is eliminated, and we will go to the next round, that is we will go to I2, alright. So shall we retain this fellow? Shall we go to the other portion of the board? Okay. Now conduct the 2-point test. Let us say the region to the left of x2 can be eliminated. Okay. Now we are left with x2 x equal to b, right, correct. What is this interval now? I1, correct. This fellow is I1, the new interval of uncertainty is I1. Now we choose 2 points x3, x4, okay. Such that they are at a distance of I2 from the 2 new ends. Okay. So what is our friend I2? What is our friend I2 himself? I2 is I1 into right. You remember in the last class we took 5 by 8, the next one was 3 by 5, next will be 2 by 3, you have to go backwards, okay. So now we do not have to leave him like that, we can simplify further. So I2 that correct? All right. Now, so I2 so what is the equation number we stopped with? 4. So we will make him 5, 6, 7. So the time has come to erase this portion of the board, I think. So x3 equal to x2 plus I2, x4 equal to b minus I2. Please watch carefully. Is that fine? Vivek, is it fine? So x3 is the point from this end is the original point x2 plus I2, x4 is at the same distance I2 but from the other side, it is b minus. Okay, now this is equation number 8 and 9. All this labor is to prove that one of the 2 points is already there. I already demonstrated with the numerical example, but I wanted to do that with algebra so that the proof is clean. Okay, yeah, so it is good to have this in the notes. It is very difficult to find it in textbooks. Okay, so people will say it can be shown asymptotic convergence and right. X4 is x3 is equal to x2 plus I2. Now let us substitute for x3. What is x2? What is x2? A? No, we simplified, no? A Fn minus 1 plus b minus a do some things get cancelled? No hope, this is not the point. I am interested in x4. I do not like him, so I just leave him. So I will go to x4. Okay. Anyway, this is a new point, right? Okay. x4 is b minus I2. x4 is fun. So b minus right. Now I can substitute again for Fn. What is happening now? X4 is b Fn minus 2 is equal to x1. Huh?
Bfn minus
Yeah, 2 is anyway.
AFN minus 2
Plus AFN minus 2. Yeah, BFN minus 2 gets cancelled. So this is x1. All right. Therefore, what are the 2 points x3, x4, only one is really new. This happens iteration after iteration. that contributes to the power of the method. 1953 it was figured out, it was a big rage, no, it must have been a big rage at that time. Now it is so obvious to us. What is obvious to us now may not have been obvious in the past, okay, and what is obvious at 8 am may not be obvious at 1 pm after lunch when you attend the same lecture. Okay, so what is the reduction ratio of the algorithm? So what is the reduction ratio of the Fibonacci search method? What is the RR of the algorithm? I naught is B minus A. Correct? Will it become 1 in the end? Should become, because the first and the second number of the Fibonacci series 1. Therefore, RR the Fibonacci number itself is the reduction ratio of the algorithm. So how do you start with? Suppose you want to find out for the cylindrical water storage problem, solar water heater storage problem, the original interval of uncertainty is 3 meter, you want to have an uncertainty of 0.15 meter, the reduction ratio is 20. If you have a reduction ratio is 20, you have to look for the nearest possible number for the Fibonacci sequence. What is the nearest number? You should take the next higher number, not the lower number, 21. Okay. So if you take, if you start with, so if it is 21, this n also approximately gives you an idea of the number of functional evaluations. I think you will have to do n plus 1 evaluations. Can you correct me if I am wrong? Correct? So you have to do n plus 1, not n, because the first time you are doing 2. Okay, so you will get an idea of how many evaluations are required, what is the final accuracy. This is the way the algorithm works, and you can compare now. I have given you 3 algorithms: exhaustive search, dichotomous search and Fibonacci search. For a good number n equal to 14 or 16, you can see that the Fibonacci will just whiz past all the others. What is the 16th number of the Fibonacci? Some crazy number, man. So okay, so this fellow will x1, x2, x3, x4 exhaustive search, and you will see all the things, and then finally reduce it to 1/16 or 1/8. 1/8, it will reduce to 1/8 of the original interval. So revisit the solar water heater problem. Now why I am doing that is there is some there is a consistency check for the same method. We will change the problem after we move over to 2 variable problem. For single variable search technique, we will stick to the solar water heater problem, right. So Monday is the quiz, right. So we will have 3 questions. The paper as usual is very long. I already said it yesterday, so all the best. So it took 7 hours for me to set the paper, not to solve the paper. I wanted to ensure that that any of the algorithms you develop to beat the system don't work. Okay, so what is the problem number? 35. So it should be n plus 1, man, Vikram. 34, okay. Cylindrical, solar So for the cylindrical solar water heater storage problem, how do we give this n, because I want you to do the same thing as what I have done so that we can compare. So execute the Fibonacci, execute the Fibonacci search algorithm for the cylindrical solar water heater storage problem. Execute the Fibonacci search algorithm for the cylindrical solar water heater storage problem with the original interval of uncertainty being 0.5 to 3.5 meters. Perform 7 function evaluations. Now this is for classroom, right, do not worry. Perform 7 function evaluations, that means f of n, you have to perform 7 functional evaluations. So I will also say that perform 7 functional evaluations. Start with f of 8, start with f of 8, understood. Start with 21 by 34 on both sides, because you can compare with, after 7 evaluations you will hit the center. If you do not like, you remove that, do 7 evaluations, start with f of n equal to 34, okay, that also is alright. Start with f of n is equal to 34. So take the original interval 3 meter, f of n minus 1 by f of n is 21 by 34. So 3 meters into 21 by 34 will be your I1. Take I1 from both the ends, 2 points, calculate the value of A at both the points, see which portion of the interval can be eliminated. So A, okay. So first step, please write the series so that you do not forget it, right. So you have to go backwards, right. Please first write the series and then draw the original interval of uncertainty, and it is not the x, it is r, right. So r equal to 0.5 meter, r equal to 3.5 meter, I naught equal to 3 meters, I1 how much is this? 1.85, okay. So choose 2 points, x1 is 2.3, 2.35, x2 is how much? 1 point, is it 1.15? 1.65, correct. Do not worry that x1 is more than x2, do not worry about this. We have this thing, our notation is whatever point is chosen from the left interval is x1, whatever is chosen from the right interval is x2. Use your common sense, do not get worried about whether x2 can be on the left of x1, do not worry about this. If it is confusing, you change x1, x2 accordingly, right, but be consistent. Vaibhav, is it okay? Fine. So now get A of x1 and now A of we should not say x1, right? What is it? It's not x, it's r, or you should change the radius itself to x in the original, in the first place, right? So we will stick to r1, A of r1 I have the solution with me, but I want you to solve along with me. So A of r1 38.1 meter square, correct? Okay. A of r2 21.95 meter square. A of r1 is greater than therefore region to the right of r1 can be eliminated. Is that right? Therefore region to the right of r1 can be eliminated. Abhishek, is it fine? Okay. Okay. What is the new interval now? Yeah, what a new interval to the right of, so r equal to 2.35, right? What is I1? 1.85 meter, right? So we now take 2 points x3, x4. These two are at a distance I2 from the two ends. I2 equal to I1 1.85 13/21. Yeah, so we are first we took 21/34, now we do 13/21. So you move from the right to the left till you hit this, where you now towards the end, when you reach the end, the 2 points xn and xn plus 1 will be at the center, right? That is where you stop the Fibonacci search. Clear? Okay. Now, how much is this? 1.15, huh? We will adjust it, adjust this such that one of the 2 points is equal to. There may be some small problems with your decimals, but do not recalculate. I mean, because originally the algorithm tells you that one of the 2 points must be a whole point. Okay, so why I am writing x? Why am I doing this? R1. Yeah, please tell me R3 equal to R2 plus I2, R4, what is this? R1, right? Right? R1 0.5 plus this is 1.65, this is
1.20.
1.2 21 1.20, then we leave it like that, 1.20. No, sorry, this is correct, no? A plus I, this is correct, R1 minus I2 is correct, okay. So now R3 is equal to R2, right? Is that correct? R3 is equal to R2. So that point we already know. So A of R3, A of R3 equal to 21.95, correct. A of R4 must be smaller, huh? 15.7. Where is R3 now? Therefore, region to the right of R3 can be eliminated. Robin, is it correct? Region to the right of R3 can be eliminated. So R equal to 0.5, stay with this. R3 is 1.65, I2 is equal to 1.15. So I now take 2 points R5, R6, okay. So R5 0.5, 8 by 13, R6 what are the two values? R5 is 1.15, 1.2, this is
0.94.
9.4. We know the solution is 0.866. So I know that A of R6 is less than A of R5. I don't have to do, but you have to do. Okay, we know what the answer is. So whether you do it as a part of a project or exam, it is very easy, but you have to be systematic and methodical. You cannot get impatient, you have to do it patiently. It is not such a brain teaser that you cannot solve or something. If you are systematic, you will get it, okay. Do not be in a hurry, you do it slowly without making mistake, you will be home, right. So A of R5 is already there, he is already there, 15.7. But now I have a of R6 which is lower than him, I hope so, 14 point, therefore region see you will keep on eliminating to the right because the answer is close to the left interval, you will keep on chopping off from the right side, okay. Region to the right of right. Now R equal to 0.5, R equal to 1.2, I3 equal to 0.7, correct. Yes, now take 2 points 7 and 8. So R7 0.5, to 5 by 8, right? Point 94. Okay. Please note that in every iteration one of the points is already the previous point. So though you seem to be working out a lot, your functional evaluation is, in this case it so happens that the functional evaluation is easy and the other steps seem to be as difficult or as laborious or as time consuming as the functional evaluation. Sometimes the functional evaluation may require the solution of a Navier-Stokes equation, or you have to solve some using COMSOL multiphysics. In this case it was so simple, 2 pi r square plus 8 by r. So then the other steps will be ridiculously less time consuming compared to the functional evaluation. Okay. Now A of R7, we know that 14.1. I know A of R8 will be greater than this fellow, it will be some 16, 17, 18, 14.2. Oh, then we have to be careful. Now region to the left, region to the left is eliminated, therefore for a change we got rid of the 0.5, right. I expect you to solve a problem like this in 15 minutes if it is 7 or 8 evaluations. To 15 minutes, you can do it if the evaluation is not painful. Okay. So now what is this? Left side
0.76.
0.76, what is the value? R? R6, R7, what is it? R8. This fellow is R5, he is 1.2. I4, 0.44. R9, R10. Three by 5. Yeah, tell me. 1.02.
0.95.
0.94. A of R9.
14.38.
14.1. Region to the right of R9 can be eliminated. We are close to the final point. How many have we done so far? 6. 6 evaluations are only one more. Okay. So region to the right of I hope all of you are able to follow. Why am I removing region to the right of R9? Because 14.38 is more than 14.1. We are solving a minimization problem. Now, so what do we have now? R9 is 1.02. You already came, is it? What is it? Okay. I can't ditch that. R8. Yeah. R9, right? How much is this? 1.02. Okay. So I have I5. 0.26. So I have 2 points, R11 and R12. So R11 equal to 0.76 plus 0.26 into 2 by 3 R12 equal to 1.02 minus point into 2 by 3 0.94, 0.84. I hope everybody is following this. Okay. So what is A of R11? 14 point. A of R12 should be more. Huh? Oh, okay. That is closer to the answer. 13 point. So A of the region to the right of R11 can be eliminated. So we have 0.762 R11, right? Is that right? What is R11? 0.94. .18, I 6. The next point will be the center. We can't do much with that. The buck stops here. So the next point is 0.18985 R13 equal to R14 equal to, so the final interval of uncertainty is 0.18 meter. The solution is now lying between 0.76 meter and 0.94. With just 7 functional evaluations, you are able to reduce the final interval of uncertainty to 18 centimeter from 300 centimeter. So you got a remarkable reduction ratio, which is how much? You got an RR of the RR now. So final interval of uncertainty. So RR is, that is how much? 16. What is the theoretical RR? 34. What is N? Huh?
7 evaluations. 21.
Theoretical error is how much? Fn. So what is the problem now? In fact, you stopped at 6 evaluations, I think. We stopped it, we can go for one more, you can go for one more and have a 3-point test. Okay? Or you can go for one more, have a 2-point test between these 2-point tests. It is equivalent to the 3-point test. If f of x1 is greater than f of x2 but is less than, so you can still bracket the interval and bring it to half, which will make it 32. So you have to go to the last step, right? If you want to, so we can, are you getting the point? Except that instead of 2 points you will get 1 point, so you have a 3-point test, right? 3-point test also I told you, right? Otherwise you can stop here. So you will get something which is smaller than what is predicted with the reduction ratio, theoretical reduction ratio, the algorithm, but which is much superior to what you will get using exhaustive search. If you use exhaustive search, your final interval of uncertainty will be 1 meter, right, after 7 evaluations. N plus 1 by 2, how much is it? 8 by 2, 4. So you will have a final interval of uncertainty of 75 centimeter. It will be superior even to the dichotomous search. But now there are some higher order searches which can do better. For example, after you have reached the center point, it is possible for you to get R3 is equal to R14, which is already there. R13 is equal to R14 was already one of the points. If you have these 3 points, now if you are pretty confident that you have bracketed the roof, you have bracketed the minimum and it is indeed lying between 0.76 and 0.94, it is possible to use the Lagrange interpolation formula and have a local polynomial connecting these 3 points and then make that fellow stationary, dy by d, dA by dr equal to 0, and then he will give you the correct answer. Okay, but so much it is a overkill for us for a stupid problem like this, but it is possible.
When we are writing the program, how do we decide that we take till f8 or till?
I have to do that. If I take fn is equal to 34, I have to do the last iteration. So let us say that if both the points coincide, we do the evaluation and take the 3-point test.
So I think we have some desirable accuracy required in the problem. So for
Here
that,
desirable accuracy required, you take n plus 1, go to the next. If you have desirable accuracy required, if there is a, go to the next nearest Fibonacci number so that this half problem does not arise, then you will land. You can work out the problem that way. What is your desired level of accuracy for this problem? Suppose you declare that the desired level of accuracy is 0.15 meter, then you divide 3 meters divided by 0.15, 20 reduction ratio. For that calculate the corresponding Fn, and since you now know that the Fibonacci, the last 2 points will give you trouble, go to the next Fibonacci number, that is all. Okay, because the Fibonacci seems finally ends up with one point where you have to use something other than the 2-point test to reduce the length of the interval. It is possible still, it is not illegal for us. You can do one evaluation and decide where it will lie. So you will decide either it is lying here or here, right? Fine, okay. So we will stop with this.